Hi, I'm Brendan Minish, the CTO of Westnet. Westnet's actually a wireless internet service provider based in County Mayo. Mayo is a large rural county in the west of Ireland, so we have quite a bit of experience with deploying wireless service across water, because we have customers on offshore islands and we have customers on inshore islands, and also in coastal areas people tend to build their houses with a view of the sea, which gives you some chance of getting a radio path into them, but cross-water wireless links are not without their problems. So back in 2011 I was approached by the Irish Marine Institute. This is a research buoy. They use these out in Galway Bay at the moment, but they're deploying them in other places as well. And these are used to carry out various science projects. The project they were working on in this instance was recording underwater whale and dolphin sounds, and they put down arrays of hydrophones from each of these buoys, and with use of multiple buoys they can actually track the whales and dolphins over quite a large area, see what, where they're moving around and everything. And it generates a lot of data, which they'd been solving up until now really by recording to hard disk and then going out and collecting the disks every couple of weeks, but this really didn't give them any kind of live view of what was going on, so they wanted a wireless link. So I met with them and I asked them sort of what they wanted us to look at doing. So the first thing they said, the link would be about 5 kilometers, and they wanted an average throughput of 15 megabit per second or better. They were planning on continuing recording to hard disk, so they had the ability to catch up if you take hits in the link and things, but that was the average speed they needed to stay on top of things. And they wanted high link availability, which made me extremely nervous, because in the telco world, high availability takes you into sort of 99.99 something %, and this just really wasn't likely to happen here. But when I pressed them a bit on this, they actually said 90% was in their book high availability, so that softened things quite a bit. So I was quite pleased to hear that. They have a DC power budget on these buoys of around 200 watts. The buoys themselves are powered by solar panels, and then they have rechargeable battery banks. So they have a 24-volt DC system, and everything that's connected to the buoy has to come in at under 200 watts, otherwise they're using it up faster than they're making it. And they wanted to do this within the license rules for the upper part of the 5.8 gig band. In the Republic of Ireland, we're allowed 2 watts EIRP up there, subject to notifying the regulator, so there's a little bit more power to play with, which eases things a bit. So in looking at it, I figured there were 2 problems to solve. The first is trying to get the wireless across water to behave well and be reasonably stable. It's a really tricky business, and we had learned kind of a lot of stuff the hard way, I suppose, in Westnet on this. But in our case in Westnet, where we're dealing with coming off fairly high sites to customers that were also reasonably high, but in this case we're dealing with something that's right at sea level, so it's a different kettle of fish altogether. And then there's the problem of antenna aiming. You've got a buoy out there that's moving quite a lot, and you've got to try and keep the antenna on the buoy aimed at the shore side. So I figured to break this into 2 problems. We'd look at the wireless side of it first, and then maybe by the time we'd finish with that, we'd have some ideas on how we might deal with the antenna aiming problem. But at least by breaking it up, we weren't dealing with both of them at once. So just a little bit of wireless 101 for those of you that aren't terribly familiar with wireless. This is a typical terrestrial path profile, and you'll see the green line in the center is the optical line of sight path. Radio is just like light. It's electromagnetic radiation with a much longer wavelength. And just like light, we have Fresnel effects. When something's crossing an edge, it tends to get refracted or bent. And in radio, this causes huge problems for us, because the signals that have been refracted or bent often arrive at the receiving end, but they arrive on having taken a slightly longer path. So they're now out of phase and they interfere, and you get constructive and destructive interference, and it causes all sorts of problems at higher data rates. So in terrestrial planning, we generally don't care too much about occasional Fresnel zone incursions, as long as they're outside of the first Fresnel zone. Actually around 0.6 is where we start to get really worried about it. But I just wanted to show that there. And of course the other problem in wireless is that the laws of physics are sort of against us from the beginning, that the big dominating factor in path loss is the free space path loss, which follows the inverse square law, because again, think like light, its power density falls off with the square of the distance. So this means the typical sort of path loss you can expect on a 5.5 kilometer link would be about maybe 123 decibels. It's a lot, and compared to, fiber guys have it really easy. They've got a guided media. What they put in there doesn't escape. And of course it may be a lot larger than this on paths that are partially obstructed, have Fresnel zone issues. But water is a bit different from the normal Fresnel zone issue, because it's highly reflective to RF. So effectively the radio energy that's impinging on the water is going to get reflected, and certainly around the middle of the path it's going to tend to get reflected in the direction you really don't want it, i.e. towards your receiver, and it'll arrive having taken that slightly longer route and be out of phase and cause all sorts of problems. So the problem anyway with cross-water links is getting them to work stably, and link stability is very, very poor due to these strong reflections. Now, it's worse in stable sea conditions, because when you have stable sea conditions, the sea is not nearly as randomized, so the reflections that are happening are statistically more likely to go in the directions you don't want them to go, i.e. towards your receiver. To combat this, you use spatial diversity. And in spatial diversity systems, what you do is you stack 2 or more antennas vertically spaced at each end of your link, preferably, and the radio system then votes or chooses which one of the paths is giving the lowest bit error rate at any given time. And some of the more sophisticated modern systems will actually build a good path out of 2 bad paths. So for testing, because what the Marine Institute were asking us to look at here was very low to the water, it's quite different from stuff we'd done, we needed a couple of cross-water paths that we could test on. And we want to be able to do this under variable sea conditions, because getting something to work well on a calm day wasn't necessarily any guarantee it was going to work in rough weather and this kind of thing. We wanted to be able to do this without getting onto boats. I mean, boats are one fine way of doing it, but then you're straight into the antenna aiming problem as well at the same time, and we definitely wanted to avoid that for as long as possible. And the other element, of course, is we wanted to test for fairly long periods of time. So I was able to identify 2 paths in Clew Bay. Clew Bay is a big bay in County Mayo, and these sites were both from piers. So we had a 5.5 kilometre path from Old Head Pier to Lecanvy Pier. And interestingly, we also spotted a 13.25 kilometre path from Old Head Pier to Mulranny. And this was a very useful find for us, because what we were trying to do was work out what tunables would make the most difference in terms of achieving stability. So starting off with a path that's quite a lot longer and a lot more marginal than the one we were trying to optimize for meant that we could drill down quicker to the things that mattered most. So in fact, we did much of the testing on the longer path. Also, there was a need to log data during testing. A pretty simple setup for this, really, a virtual server running CentOS. I used Xenos to graph SNMP data. Really the only tunable there was I changed the polling intervals to be much shorter, so I was getting a bit more resolution on it. Splunk to ingest the systems logs in case they showed us anything interesting. They didn't really, but we had them anyway. And the other thing about this as well is by virtualizing it, I used VMware, but the Marine Institute themselves have a good VMware cluster. So the hope would be that when we finished sort of the first round of trials, that we'd have a platform for monitoring that we could just drop straight into their system, no need to rebuild it. Used Linux laptops at both ends, and we used iPerf for testing. Now, the application itself was TCP based, so we used that to test, and the data flow was very asymmetrical, that most of the data would be coming from the marine end, the buoy end. So that was the traffic flow direction that we tested in as well, to try and replicate as much as we could what it was going to be used for by the end user. So here's a couple of the paths. This is Old Head to Lecanvy, and you can see once you've come off the beach, you have water there under the middle of the path, which is the most important bit really in terms of where the reflections are going to occur. And here's a radio plot of the path. This is a tool actually we'd use for doing terrestrial radio plots. And the brown is terrain, and then the red line there is actually the curvature of the Earth. And you can see even at that short distance with the low heights involved that the curvature of the Earth is apparent. The pink line is the 0.6 Fresnel zone, which is when you're doing a terrestrial link, is when you really start to worry when you have incursions in that. So you can see the water is very deeply inside that Fresnel zone. There's a lot of energy liable to impinge with the water in that kind of setup. And there's the actual optical radio path in the middle. And here's the longer path across Clew Bay from Old Head to Mulranny. This, by going straight across the bay, this bay is facing westward, so we have full Atlantic Sea rolling in here, swells and interesting sea conditions, whereas the path across the shorter path will be a bit sheltered by the way the land is set up. And here's the plot on that one, and as you can see, we actually ended up raising one end slightly so that we did have this optical path, the line of sight path between them. But again, we felt this was fair because in an actual buoy deployment, the land end would be much higher above sea level than what we were testing here. We were really trying to come up with worst case scenarios so that we could work out where we'd have the most effect on the tunables. So here's a couple of pictures of the test setup. This is representing the land end, and what we were doing here in particular was we were playing around with spacings. That pole there can telescope, so we can raise up and down, and the top aerial there is horizontally polarized, and That one's vertically polarized. Now, the CPE device we're testing didn't have the ability to have two aerials. In fact, this would have been problematic in the buoy. It had a single aerial, but it operated in dual polarity. So to have two usable paths for diversity, seeing as we're only doing the spatial diversity at one end, we would have to also use polarization diversity, and that's what we did. And then the other shot shows some spacings that we were trying out on the much shorter link, where we were finding we were getting away with much narrower spacings. And this is one of the shots of the CPE device that we were testing at the Lecanvy end. It's looking towards Old Head, which you can see is there. Out there somewhere is Clare Island, where we have quite a few customers in the ISP space. Some served from land and some actually from a point-to-point linking equipment on the island. This is a fairly typical sort of low-cost 5 gigahertz CPE that's used in the WISP space. It's waterproof for mounting outdoors, but it sure isn't marinized. It would have to be fully marinized before going on a buoy. But at least it's light and small, so you're starting from a good position. So at 5.5 kilometers, after a bit of tuning up, we did really kind of well. We averaged 37 megabits per second. We did have a small hit, but it wasn't a full dropout. These sort of things can be expected in cross-water paths. And yeah, it performed pretty well. Now, as you'll notice, there's a graph here, which, like all good graphs shown at these sort of things, goes up and to the right. Does anybody know why it goes up and to the right? You're all very silent. It goes up and to the right because we started testing at high tide. And as the tide went out, the water became lower and lower onto the path. So the path had better and better clearance from the sea. Now, we started at high tide because, again, I'm a pessimist. I really like to go and see if we can get something going when it's not going to. And as the tide went out, there's probably 4 meters of tide nearly in that bay. So there's quite a bit more clearance as the tide goes out. And again, here's some results on the 13.25K link. Now, there were a couple of hits on it, not full dropouts, but periods when it really couldn't pass much. But we averaged 24 megabits per second. We did very well at that distance. The signal strengths there on the graph are pretty marginal for that type of equipment, so it's right on the ragged edge of working, really. At the beginning of the signal graph, you'll see there's a bit of an uptick, and that's because we, on the shore side, would have to apply a power reduction to stay within the rules due to the antenna sizes we were using. But we didn't do the power reduction until we'd finished the lineup, so that's where we applied the power reduction. And again, you can see the impact of the tide going out. So I guess what we learned was how to do this relatively stably close to the water. I'd hesitate to do this in the ISP space because, we felt that we got to about 99%, but I don't think customers would be very happy with that. But it meant we had a bit in the bag. In terms of doing spatial diversity, though, if you can only do it at one end, you have to use about 4 times the spacing at the other end. And this is a matter of geometry because it's in the middle of the path where most of the reflections are occurring, and you're trying to create as much difference as possible between the paths at that point. We were using kit that was using Atheros 802.11 chipsets, 802.11n chipsets, and we found a few tricks. Now, this may be somewhat vendor specific, but what we found with these devices, that if you stop them doing 802.11n, where as soon as the chipset sees that it's got 2 paths, it tries to use them differentially to carry data, and we restrict them to A mode, but enable both chains on transmit and receive, it actually sends the same data on both chains. So now you've got exactly what you need to be set up for diversity. And also on the receive side, they seem to be actually using both paths to build a good constellation rather than just doing an A or B vote on which one's the least bad. So, with this kit, we were able to get away with much narrower spacings than we would have typically had to use with licensed point-to-point microwave kit. Obviously, you have to enable both chains. And spacings of several meters. Generally for the ISP space stuff we've done, we're dealing first of all with stuff that's 20 or 30 meters at least above water at both ends if we can manage it. And even there we'd use spacings of 2 to 3 meters at both ends. And vertical performs much, much better than horizontal across water. And this again is back down to radio being electromagnetic radiation like light. What happens with the vertically polarized waves, as they impinge on the wave surface, they tend to dig in slightly and get absorbed, and the horizontal polarized waves get reflected. So what happens is the amount of multipath you see in vertical is much reduced compared with horizontal under most sea conditions. In fact, if you've used polarizing sunglasses or a polarizing lens for your camera, you will have seen this when you've moved it around to take the glare off water. It's exactly the same thing. And lastly, again, in the ISP space, if you've got to go and build a cross-water wireless link and, you can't talk your manager out of doing it, use local terrain. And what I mean by that is, again, you'll be using spatial diversity, but what you might be able to do is place the lower of the two aerials low enough that some of the terrain locally is occluding its view of the sea, because that will cut down on the amount of multipath reflections that it'll see from the water and really help with getting everything nice and stable. So this left us from the Marine Institute's problem with the other problem, which was antenna positioning. On the land side, of course, this is fairly easy. You just bolt everything to a building and it's kind of job done. And, you know, the buoy end, however, is a different story altogether. Here's a picture of one of these buoys in Galway Bay. Now, the top deck here is about 2.5 meters above the float, and those are footholds for climbing up the inside to get at the roof, and you can see the solar panels and everything. Funnily enough, I couldn't find very many pictures of these in bad weather. Like something to do with people not wanting to bring the camera out, I suppose. A couple of the guys who worked on these have said that being inside one of these in bad weather is quite challenging. It's you know, one of those occasions where it would be wise not to have had lunch recently. Here's a picture of a NOAA weather buoy out in a force 5, 4 or 5. It's not particularly heavy sea. But there's one of those anyway, and here's another one in some reasonably rough weather. So they do tend to move around a lot. So I got in touch with the Marine Institute and asked them, did they have some data on the types of movement that these buoys do? And they do, because they have, being a research organisation, they put sensor packs on them and things. So in looking at the data, we found something really interesting, or at least it was new to me, and they roll a lot, you know, really, you know, almost knocked flat in very heavy seas, and they tip from side to side, not quite as much as they roll. But what we did find is they didn't rotate very much. They rotated sort of plus and minus 30 to 40 degrees of a central axis, and this really surprised me. So I asked them about this, and they says, well, it's to do with the way they're moored. And the reason we do this is that we have our own stuff on the seabed, and we don't want to get all the wires tangled up. So you've got two big heavy mooring blocks and really heavy chains, and this leads to there being a lot of horizontal pressure through the buoy, and this keeps it from rotating a whole lot. So this kind of opened up some possibilities. Now, in terms of antenna positioning, here's one solution. This is the BAT system that's used for satellite dishes on boats. They're very good. They can keep a satellite dish aimed at a geostationary satellite off the deck of a moving boat, but they have a couple of problems here. They work by having two very high torque stepper motors that are constantly moving to do the station keeping. So in terms of power, they're very hungry. These things use 200 watts plus on their own, so there goes the power budget. They're also kind of expensive. But we'd been testing a low gain CPE device which had a wide tolerance for aiming, and what we found at 5.5 kilometers, as long as we were making up the gain on the supposed land end, that we could tolerate about 150 degrees of arc off axis. And it's also a small size, and it was lightweight, and it had low power consumption. It drew about 8 watts at 24 volts, so that was ideal, really. Now, the reason for this sort of wide tolerance for aiming, here's the antenna patterns from the small device, and as you can see, they've got substantial side lobes, and the gain does not fall off very rapidly from the center line, and that's, of course, the trade-off. Gain is got by focusing, so if a device has fairly low gain, it, by extension, has a pretty wide antenna pattern. So if we've got high gain on the shore side, to maintain the required system gain, that means larger antennas than one would normally use at that distance, but, you know, for something like this, it's not an insurmountable problem. There's a much tighter aiming pattern, of course, in the higher gain antennas, but again, the buoy is doing a lot of moving around, but it's not moving around in geography. It's in one fixed place out on the ocean. So once you've done your lineup, you don't have much of a problem past that. And of course, 2 antennas required for the diversity. So we suggested 3 meters. Now, actually, I think we could have done it with less, but we kind of knew 3 was going to work, so it seemed like a safe number to come up with. And with a low gain CP and a high gain on the shore side, the required systems gains maintained, and we have this wide tolerance for aiming. And the buoy rotation is a lot less than this, so we hit upon the idea of using a gimbal. And a gimbal is a simple mechanical device. It'll take care of pitch and roll for us, and it's completely passive, and best of all, it's cheap. So that's what we did. I went to an engineer and I explained what I wanted, and he came up with this rather nice gimbal, which I'll point at. That's the hinge to the inner ring, and then at right angles you have the hinge to the outer ring. and then there's an arm and a weight, and you can see how it works. We also got a frame made up so that we could move it around and see whether there was maybe any tendency to oscillate, because if you get the weight and the balance is wrong, it might want to sort of oscillate for a long time, like a pendulum, that sort of thing. And we got this all made out of stainless steel, because again, if it worked, it was sure they might as well take it all the way to deployment. And that's what we did. We tested it. It worked. I worked with the Marine Institute's engineers to get it fitted onto the top of one of the buoys, and we tested it at sea. It provided enough stability for the link, and then after a few days they managed to persuade IBM to take a chance and put some of the live data on the system. IBM were their sort of data processing partners, and they weren't terribly keen initially to be using something that was only experimental, but it all worked. And at that point then it was a handoff to the Marine Institute. You see, to actually do this as an outside contractor for them would be quite difficult, because they have a whole bunch of health and safety stuff that applies in their field and all the rest of it. But what the Marine Institute has in its own right is very strong engineering and networking skills. They've got great guys for solving problems. Instead of me trying to learn how to marinize something or build something, I'm better off showing them and explaining and hand-holding. So that's what we've done with that. And that system, as far as I know, is still in use. I don't know whether they've deployed any more, but that's it really. And I just wanted to thank a few people, and I'll take some questions. The Marine Institute for having interesting problems, P&O Marine, who did the mechanical work on the buoy and the deployment, IBM for taking a chance, Rory Casey, who introduced me to the Marine Institute, my friend Mark McNicholas, who helped quite a bit with the trials, and John Geraghty, who did the engineering on the Gimbal Prototype, which is still working. He's one of these guys that you go to and you sort of explain a design, and he'll take it all the way to finish for you. Anyway, thanks very much. Is there any questions?
Hi, it's Will Hargrave from LONAP. It's actually a question from Dave Reeder on Twitter. He asked about, Twitter, on IRC. He asked whether the antenna, the aerial, the coax basically for the antenna, whether that affects the motion of the gimbal at all.
We actually, with the device, it was actually Cat 5 that was run up there, okay. So it's a bit lighter. If it was coax, yeah, you'd have a real problem. And I think with Cat 5, you will have a work hardening problem eventually. But I guess there's no way to do it without wires, really, is there?
Well, I suppose you could have another wireless link to the... will you do any more of these deployments, or is it just a one-off?
Well, it's kind of up to the Marine Institute now, because I spent a couple of days with them during this process explaining what we were doing. I gave them the full rundown on how to configure the devices and why we were doing things in certain ways. And as far as the gimbal goes, this is something, of course, them being Marine people had heard of that just hadn't occurred to them in this scenario. And so, in a sense, I'd love to do more of it, but for me, as a once-off project, it'd be really difficult. I mean, there was stuff like to even go out in the rib to go to the thing. There's, seafarer medical certificates and, all kinds of indemnity insurance and everything. So in a way, you're better off working through the people who've already got that, and it's adding another skill to their tool set.
Great, thanks. It was a really interesting presentation. Thank you.
Thanks.
I think this is a question which invites the answer no, but did you explore whether any of the reflections could be constructive and could actually help?
What we've found with our own experience across water is at times they will be constructive and help, and other times they won't be. Yeah. But it's you can't really predict it and say, right, at 7:15 this evening it's all going to be magic, and 8:15 it won't be. So with diversity, you're just kind of statistically spreading the problem around a bit. Yeah. And the diversity will, by its own nature, use the best path, and that may well be constructive. If it was a situation where the water wasn't moving, like perhaps across a lake, yeah, you might have different answers there. But of course, the other thing that's happening is humidity and all that sort of stuff.
Yeah.
Okay, any other questions for Brendan? Thank you very much.
Thanks.